Hello, everyone, and welcome to week 2 of lighting design in AE 311. This week, we're going to focus on vision and perception, one of my absolute favorite topics because it dovetails nicely with my research in color science. To kick us off, let's consider this image to my right here. What I want you to do is focus on the X in the center and hold your gaze for 30 seconds. If you're watching this on video, go ahead and pause now, and then you can jump forward to the next image right here, and you should see this image in full color. But of course, for those of you that didn't pause, it's not. Visual system is up to no good, and today we're going to explore some of the features of your visual system that have implications for how we design light. And I'll credit this particular demo to Josh Weedy in Psych 253, The Psychology of Perception. I highly recommend his course if you're interested in taking a deeper dive in any of these topics we're about to cover. We'll start with just a roadmap. So here are the various structures of the eye that we'll be discussing throughout the rest of this lecture. And I won't spend any time here because we're going to break this down in detail as we go along. We'll start easy with just the humors. The humors are the fluid components of your eye. The aqueous humor, first off, is a mostly fluid that nourishes the lens and the cornea. Now, in the middle of your eye, you have a more gel-like substance called the vitreous humor, which actually makes up the majority of the volume of your eye. To the outside of your eye, we can discuss the sclera, which is that tough white outer protective coating of your eye. It's also what gives your eye its mostly spherical shape. And importantly for this topic, it is the anchor for the extraocular muscles, which are responsible for a variety of eye movements. So we can take a look at the basic eye movements real quick. So when you are following, say, a pen that you move across your gaze, or a baseball flying through space, you are engaging in smooth pursuit. That's how you smoothly follow a target. That's you locking onto that to follow it with your eyes. Both eyes will be moving at the same rate as you maintain your gaze on that object. And this is a big part of our ancient hunter-gatherer instinct. More common type of eye movement that you're probably using throughout this lecture is saccades. So if you look at me and then over to the diagram of the eye to my right, what you just did was saccade over to the diagram. Now, these are extremely fast movements, and they help you form more complete images of your surroundings as your eye jumps from place to place to fill in the gaps in what you're seeing. The last type of eye movement is convergence. So if you take your pencil again, you move it towards and away from your face. When your eyes are crossing and uncrossing, that's convergence. And that's how you can bring your gaze into something very close to you or outward at something very far away. Moving on to the process of accommodation. So there are several components of the eye at play in accommodation, starting with the cornea, which is important because most of the refractive focusing power, as in most of the ability of your eye to bend light in and focus it onto your retina, happens there on the cornea. Now, your lens deeper in your eye is going to provide you the variable focus. And that variable focus primarily comes from the ciliary muscles that form a ring around the lens. And those muscles are going to stretch and flatten the lens to view objects further away, or relax and allow the lens to become more oblate to focus on things close up to you. So these components taken together The purpose is to focus light onto the fovea in the center of your retina, and that leads to accommodation, or the rapid changes in the shape of the lens that focuses images onto your fovea. And this is happening all the time. In fact, it happens basically within your saccades. Now, there's a variety of ways that accommodation can break down, starting with astigmatism, which is just an irregularity in the shape of your lens, which causes fuzziness in how that image is projected onto your retina. There's a variety of ways we can solve this nowadays. One of the more interesting things for those of you who don't wear contacts is actually weighted contact lenses. Because it's an irregularity in the surface of your lens, those contact lenses are going to be customized for the specific wearer. So they actually include a little weight so that the contact will rotate down and always be in the same orientation within your eye so that it is adjusting for the specific irregularities as opposed to more general irregularities such as myopia. Now, myopia, or more commonly called nearsightedness, is an accommodation error common in young adults, and it makes it hard to see distant objects because light focuses before it reaches your fovea instead of onto your retina. The opposite of that is hyperopia, which is where light focuses behind your retina. And this is actually more common in older adults. And we call that form of hyperopia presbyopia, or age-related hyperopia. And that's primarily driven by changes in your lens and weakening of your ciliary muscles that prevent your lens from fully changing shape to focus on things that are close up to you. And that's why we commonly call this farsightedness. Adaptation is crucial, and adaptation is not just one process, but rather a trio of processes that allows us to see well in a massive range of lighting conditions. Most of you probably don't know this, but daylight is actually multiple orders of magnitude higher light level than the light level that you have in a typical classroom. So, how do we adjust to this massive range of lighting conditions that we experience every day? Well, there's three ways. First off is just the synaptic interactions. In other words, this is the response of your neurons, including those on your retina itself, and they will change their firing rate in response to differing levels of stimuli. So if they're being overstimulated, they'll reduce their firing rate to prevent from being damaged. Or if they're being understimulated, they'll bump that firing rate up so that they're responding to whatever stimuli they can. A somewhat slower process that occurs over roughly a second is changes in your pupil size. And so most of you probably already know that the pupil is not so much a structure of the eye, but rather a hole in the eye that allows light to pass through the lens and onto the retina. And in fact, the structure is actually the iris, which is another muscular ring, which will relax or constrict in response to changes in light level, so that in dark settings, you can expand to get as much light as possible, or in bright settings, you can constrict to reduce the amount of light coming into your eye so that you don't damage your retina. The final part of adaptation is the opsins. So these are photopigments inside your photoreceptors, or your rods and your cones, and they change shape in response to being stimulated by photons of the right wavelength. So there's actually two processes at play here. The first, bleaching, can happen extremely quickly. For rods, that can happen as fast as picoseconds, and for cones, that's more on the order of milliseconds. And you've probably experienced this a variety of times in your life. For example, when you look directly into a camera flash and you get those spots in your, that creates an after image on your retina. And that's because At those spots on your retina, the opsins are bleached and therefore can't respond to new light stimuli. So you just see that as a white spot. And the reason that lingers is because the regeneration of opsins is actually much slower than the process of bleaching those opsins. Regeneration can take anywhere from 10 minutes up to almost an hour, depending on how extreme the change in light level is. And that's basically where those opsins are changing shape back to their original form so that they can again respond to new light stimuli. So let's take a look at these processes in a little more detail. And part of the reason why we have sensitivities to such a massive range of light levels is because we actually use two separate systems. Scotopic range at very low light levels is going to be mediated by your rods. And so you can see to my left here the scotopic spectral sensitivity curve, which is essentially just your rod sensitivity. Now, more below me in green, you can see the photopic spectral sensitivity curve. And this is actually an average of your three cones. And this is the visual range that you're most familiar with because it's the most common in most architectural settings. Photopic vision happens above 10 candela per meter squared, which is most lighting situations you're familiar with. And this is the range of adaptation where you have excellent visual acuity, good color vision, and a great amount of detail. On the other end of the spectrum, scotopic vision happens below 1/1000th of a candela per meter squared. Now, this is a lot lower than you think because when you're in fully scotopic vision, you can only see in grayscale because there's only a single photoreceptor, and color is actually the result of comparisons between photoreceptors. So think back to the last time you were seeing in black and white. Nothing come to mind? Well, that's because that 1/1000th of a candela per meter squared is actually much lower than you think. It, for example, it's starlight on a moonless night. So that's extremely dark and it's not that common. Much more common low light levels are actually going to be in the mesopic visual range, which is where you are using a combination of your rods and cones to see with. Couple important features of this plot here is the peak spectral sensitivities of these different systems. So you can see over here, to my left, the scotopic peak sensitivity actually occurs down at 510 nanometers, which is more of a cyan color, and your photopic spectral sensitivity peaks at 555 nanometers, which is more of a green color. We call this the Purkinje shift. And how this plays out in your vision is as we decrease light levels across the mesopic visual range and your rods start playing a larger and larger role, you're actually going to experience a blue shift in colors as we shift our sensitivity down more towards the blue end of our visible spectrum. Another important element of this plot is the relative sensitivity. So you can see that over on the y-axis. And right away, what stands out is your rods are actually as much as 2.5 times more sensitive than all three cones together, watt per watt of lighting. Now, that's not going to play out that often because if you had a watt of light, then you're probably not in the scotopic visual range. But this is why rods can respond to extremely dim stimuli and preserve some vision even at extraordinarily low light levels, where your cones basically don't function at all anymore. take a closer look at that photopic spectral sensitivity curve because this one is really important. In fact, we have a name for this function and we call it the V lambda function. And that's because this defines the standard human photopic spectral sensitivity. So in most visual situations, this is how we respond to different wavelengths of light. And we use this function to define the lumen. Basically, if we take the sensitivity of light at each wavelength, we can evaluate it according to the relative sensitivity over here along the y-axis, and that will give us lumens if we integrate across this function. Lumens are, in fact, the fundamental quantity of visible light as opposed to watts, which is the fundamental quantity of radiant power or just light in general. But when we're talking about vision, we don't actually care how much light we have, but rather how much our visual system responds to that light. And so we quantify that in terms of lumens. In other words, the fundamental quantity of visible light. And this forms the basis of all photometry, which is what we're going to get to next week. Clearly now we need to talk about photoreceptors since we've mentioned them several times already. So on your retina, we have a huge number of those photoreceptors, and specifically those numbers are roughly 120 million rods distributed throughout your retina and 6 million cones concentrated largely in the central part of your retina, the fovea. So there's some interesting features, let's call them features, about the structure of your retina in that it's largely structured backwards. So here's the path of light as it enters your eye. It's actually going to pass through multiple layers of neurons where your early visual processing occurs, primarily edge detection for the record. So it has to pass through these multiple layers of neurons before it gets to the photoreceptors deeper down in your retina and can there stimulate the opsins, which react with light. And if you stimulate them enough, they will change shape and transduce that light into a neurochemical signal, which is then passed back up through those layers of neurons and eventually to the optic nerve. So let's take a look at the distribution of photoreceptors throughout your retina. In particular, you have the fovea, which is the central 2 degrees of your visual field. Now that's not very big, but your fovea is very important because that's where almost all your cones are and also where the highest density of photoreceptors anywhere in your eye. So this is where most of our detailed visual processing, at least at photopic light levels, where all of your detailed visual processing is occurring. To give you a reference point, that's roughly your thumb held out at arm's length. That's not a big area, and that's why we saccade and move our eyes around all the time to fill in the missing pieces of the picture, because at any one instant, we're not seeing that much of the world around us. Now, moving away from the fovea, you can see here that the rods are actually much more concentrated throughout the rest of the retina or in your peripheral vision. Rods are much more responsive to much lower light stimuli, and they're very sensitive to movement. An example of this is when you're stargazing. So say you're out during a meteor shower and you want to see those shooting stars, you actually want to focus on using your peripheral vision to catch that movement before you snap your eyes over and use your fovea to get a detailed picture of that shooting star streaking across the sky. One more feature of this plot here is the blind spot. So the blind spot is actually where the optic nerve connects back through your retina into your brain. And the reason why it creates a blind spot is because of that backwards orientation of the neurons. So those neurons all bundle together and come to a point and then go back through your retina into your brain, creating the retinal blind spot, which is another reason why we saccade all the time, is so that we can fill in that blind spot, and your visual cortex is happy to fill in that gap for you, both by saccading and also by using both eyes to cover those blind spots and fill in the missing parts of the image so that you don't actually see your own blind spot. So here's another example of how big 2 angular degrees is. So what you should do here is focus on the X and don't move your eyes as I change the slide. Now, how many letters to the right and left of that X can you actually read? For me, at this distance, I can only get to the D and the J, or all of the letters if I cheat and saccade over to see the rest of them. But before my eyes jumped over, really, I could only read a couple letters. And that's going to depend on how far away you are from your screen. But nonetheless, that detailed vision is only happening in a very small spot. Okay. So let's tie this back into color. And to do that, we're going to have to talk a little about the path light takes before it reaches your eye. And so the first step along this process is the SPD, or the spectral power distribution, which is going to characterize how much power you have at various wavelengths across the visible range. For this example, we're using a fluorescent light source, and we're going to shine that source onto a red apple. And so instead of an SPD, we're going to have an SRD, or a spectral reflectance distribution, because this time we're not producing light, but rather we're reflecting light. If you take the product of those two things, in other words, the product of the amount of light and the reflectance of the light at each wavelength across the visible range, you will get to a reflected power distribution, which is the spectrum that's actually entering your eye. So let's take a look at those things in a little more detail here, starting with the spectral power distribution. So the first element of this plot I want to point out here is the y-axis, which is the lighting power density. So this is typically measured in watts per area, or often microwatts per area. And it's showing you how much light you have at each wavelength across the visible range, which is what we have on the x-axis. And so this is the visible wavelength. So we really only evaluate this from 780 to 380 nanometers, because those are the wavelengths we are sensitive to. Now, down here, this light source is tailing off, but because I know this is a fluorescent light source, I can assure you that it emits plenty of light well below 380 nanometers. But we don't include that in this plot because that does not affect the way we experience the light from that light source. On to the spectral reflectance distribution, we see that the power along the y-axis is now replaced by a reflectance percentage, or ratio. And this ratio will always be less than 1, because anytime you bounce light off of an object, you will get less light off of it than you put onto it. And so we can see that in the features of this plot here. And you can see below me that this red apple, unsurprisingly, doesn't reflect a whole lot of light in the blue and green wavelengths, whereas it's reflecting most of its light in the yellow and red wavelengths over here to my right. So let's tie this back to the reflected power distribution right here. And because this is the light that we actually see, the light that actually enters our eye, And what's interesting about this is it actually forms the basis of additive and subtractive color mixing. Specifically, when you're mixing color with light, you are engaging in additive color mixing. And we can see that played out in the RPD here. So these spikes, which actually represent mercury emission lines within that fluorescent light source, those spikes are going to be retained down in the RPD, and that does affect the way we experience the color of that apple. Now, over here on this side, we are engaging in subtractive color mixing because anytime you're bouncing light off of an object, you are subtracting light. And that's why when you keep adding more objects that you bounce off of, eventually you get to black. Whereas when you keep adding light, you eventually mix to white. And you can see this again played out in the RPD down here, where we have very little remaining lighting power in the blue and green wavelengths, which are primarily absorbed by our red apple. But as we cross over into the red and yellow wavelengths on the other side of this line, you see most of the remaining power in the reflected power distribution is actually there because that's what's being reflected rather than absorbed. So we have our spectral power distribution, so the spectrum of the light source. We have the spectral reflectance distribution, or the spectrum of reflected light off of the object. And then finally, we have the reflected power distribution, which is the spectrum of light entering your eye. So is this color? Probably already guessed. I'm asking the question because it is most certainly not colored. Light is not inherently colored. Color, rather, is an attribute our visual system applies to certain wavelengths of light and certain combinations of wavelengths of light. So what we need is a visual system. And the important starting point here is our three cones, which make us trichromats. Now, I'll point out a couple important features here. And that's, first off, you can see the legend. I don't call these the R, G, and B cones. And that's because they're basically not red, green, and blue cones. In fact, if you look at the red cone right below me, it actually peaks in amber. This isn't the red cone at all. In fact, it is the long wavelength cone. So we call them the SM and L cones because they are the short, medium, and long wavelength cones, respectively. And importantly, the sensitivities of these cones span a wide variety of wavelengths that are associated with a variety of different colors. So it's not really correct to call it the red cone when it responds most strongly to yellow light, and also even responds all the way down in the blue range. You can probably already see here how close these two cones are below me. The M and the L cones have a lot of overlap. Now, part of that is evolutionary because the long wavelength sensitivity cone is the most recently re-evolved cone. So we're very lucky because it's only among mammals, us and great apes, that are trichromats. Your dog, unfortunately, does not have an L cone and therefore only sees from the blue to roughly a yellow range of color and doesn't have that third cone and therefore sees profoundly less color than we do. So I will end this lecture with one parting question. Is color real? As in, is color objective, physical, and measurable independent of your mind? Most certainly not. Thank you for your time. This was Vision and Perception for week 2 of lighting design in AE 311.